Hey gang, we are here for section 8.2. I'm going to be honest, this is one of the more difficult sections to wrap your brain around, and if you've read about it, you know that. You had trouble as you were reading it. And so I'm going to try to simplify it a little bit. We'll see what happens, and hopefully it'll help out. But what it's talking about is free energy, this term free energy. And what free energy means is, if I'm looking at a molecule or even an entire cell, free energy is the amount of energy that's available in there to actually do work. Okay, and there may be some energy that's not available to do work, but we're looking at how much energy is actually there to do work. Okay, it ends up that free energy and the changes in free energy with interaction, that's going to end up determining whether a reaction is likely to happen or not likely to happen. The way the book talks about that, it says the word spontaneous. Spontaneous does not mean that it'll just happen with a flash, like boom, it just happened. Spontaneous just means that it's favorable and it's likely to happen, okay? So let's look at an example of a reaction here. And so I have a reaction on the bottom, and let's relate this reaction to this equation that you saw. But we're not going to worry about the right side of the equation here. We're going to worry about just this delta G, okay? And delta means change in, G is that free energy symbol. So what I've got is our molecules at the beginning of this reaction down here. I've written down, I just made up these numbers, but I've written down what their G values are. Okay, so the amount of free energy in this molecule is 4.5 kilocalories per mole. The amount of energy in this molecule is 8.3. If I total that up, the total amount of energy at the beginning is, what is that? 12.8. Okay, kilocalories per mole. Okay, the reaction happens in the end. Okay, there's new molecules, and here's their energy values, 2.7 and 7.4, so that adds up to 10.1 is what the free energy is in the end. Okay, well, if I look at my difference, that means that my delta G, okay, delta means change, the change in G is going to be 1.7. I think that's right. Excuse me, 2.7, I can do math. It's going to be a difference of 2.7, okay, and we've lost that energy, it got lower, so it's going to be negative 2.7. Okay. What that means is that in this reaction we lost some energy, so actually some energy is going to be released. I'm just going to put an E here for energy, but oftentimes it's released as heat. Okay, and heat is kind of lost energy in a cell usually. But anyway, so this has a negative delta G. Okay, and the way that happened was it lost energy throughout the reaction. What they found over years and years and years of experiments, as the book puts it, is that if you've got a negative delta G, so a negative delta G, that means that the reaction is spontaneous, which means it's favorable within a cell. It'll just kind of naturally happen without much work from the cell to make it happen. If we did this reaction in the reverse and went this way, okay, we would have a positive delta G of 2.7. If we have a positive delta G, it ends up being not favorable. Check minus here. Means it's not favorable. That's probably the biggest thing you need to know from this chapter, is if there's a negative delta G, it's good. If there's a positive delta G, it's bad. Okay. The reason for that, and actually before I go into the reason for that, I'm just going to talk entropy here for just a second. Entropy is disorder. And what we will see is disorder. Disorder is good in nature, and if we can increase disorder, that's that second law of thermodynamics. As things become more disordered, that's natural. Okay, and so one way to give a negative delta G is to increase entropy. If I look at my equation here, if I got a really large number right here, that means I'm going to take delta H, which is the total energy, and I'm going to end up subtracting a larger and larger number from that, which increases my chances of getting a negative delta G. Okay. To explain this a little further, I'm going to pull up a diagram from the book, or a picture from the book. There it is. And what this does is it shows a couple different scenarios where we start out with something that has a lot of energy stored in it. Okay, a lot of energy, and then a natural event happens, and it makes less energy and less free energy. Okay, another term that I'm going to put in here is stability. The idea of stability. If we look at this diver up here, he's on top of a diving board, and being up there is a less stable position than if he's in the water. Okay, and if we remove him from the diving board, he very naturally falls down. Okay. If we look at potential energy, up here he has a lot of potential energy. Once he's in the water, he has less potential energy. So there's a loss of energy. That's a negative delta G, and this happens very naturally. Okay. And what's happening naturally is he's going from an unstable place to a stable place down in the water. Closer to the ground you are, the more stable you are. Okay, that stability, what we find is one way you could say is if I've got a high G, so if I have a large G value, then I'm less stable. If I have a low G value, I'm more stable. Okay, another place we can look at this. This is supposed to be food coloring or dye or something like that placed in some water, and you put a drop of food coloring in water, and it's very organized. Its entropy is very low. Okay, so it's very organized, and as it's organized in one spot, it's actually very unstable. There's lots of energy there. G, there's a high G value because it is organized, and over time it will very naturally change, and the molecules will spread out, which makes more entropy, but it also makes it more stable. The way I know it's stable is once dye is completely spread out inside of water, it doesn't have any overall change anymore. It reaches equilibrium, which means it's stable. Okay. Another way we can look at this is we've got a large molecule being broken into its smaller pieces. Okay. Here it's very organized. Up top it's very organized. On the bottom it's less organized. Up top it has lots of G, lots of free energy. In the bottom it has less free energy. Okay. On the top that means it's not stable. A lot of energy means it's less stable. Down here it's more stable. Okay, and so this one would have a negative delta G as well, and that happens more spontaneously than if we did it in reverse. Okay, so this is this G values delta G, but we've got more energy. So just kind of recap: more energy in something means it's not stable, and naturally things will try to move to a stable position. They will do that by losing some of their energy. Most of the time when they do lose energy, it's because they're increasing disorder. Okay, and as a result, they're going to lower their G value or their free energy. So that's that slide. That took me a little while to explain. I'm gonna talk for another 4 or 5 minutes here probably about how to apply this to reactions that actually happen within the metabolism of a cell.